Yeah, so thank you very much for the invitation. More than a talk, it's really a discussion. So as you will see, there is no conclusion yet. So we've made some progress, but we don't have a broad overarching message that we can share at the moment. So you will see that the talk will go as follows. So let's say the concrete part is that there are some well-known dualities on the lattice, and we're trying to study their continuum limit, but away from the critical point. So at the critical point where these theories are well described by a CFT, all these discussions that we're going to have is well known. A bit away from the critical point, it's well known on the lattice, but as far as we know, it's not fully described in the continuum. The reason for doing that, let's say the broad motivation is to solve the hierarchy problem, the one of the Higgs boson mass. And so you'll see that the talk will go as follows. I'm going to start by giving you a very broad introduction to the problem, because probably some of you don't think about it very often. Then I'm immediately going to tell you why this story is not just going to work out of the box and might just never work to solve the problem. But then after that, we're going to get to the concrete part, study these models in the continuum, and see that probably, maybe, we can get some interesting statements out of them, even if they're not necessarily going to be explaining a mass hierarchy in quantum field theory. Okay, so this is the outline, and a bit more precisely, so I will start with the hierarchy problem, and then I will discuss the transverse Ising model in 1D. Just because of the usual analogy between classical statistical mechanics in 2 dimensions and quantum mechanics in one less space dimension where the other one becomes time. I'm going to talk about this model just because there the duality is very manifest. You can just see it concretely in 2 lines using the algebra of the Pauli matrices. But then we're going to see also that this model has a continuum limit that doesn't look at all like a relativistic quantum field theory, so it's not really what we're going to care about in the end. And after that, we're going to do the 2D classical Ising model, and we're going to see that this one instead maps to a quantum field theory that might be interesting. And I'm not, I mean, when I say quantum field theory, I really mean quantum field theory. So I'm going to match the generating functional of this theory, the classical statistical mechanics theory, to a quantum field theory problem, so to the generating function of another quantum field theory. And you're going to see that, I mean, for all practical purposes, I'm just going to make my life harder. Okay? So the quantum field theory that corresponds to the lattice theory is way more complicated, and maybe we're never going to be able to do the calculations that you would like to do, but I think it's a worthwhile exercise, because even if it's high risk in some sense, if it works, we're going to have discovered some new dualities that were not immediately obvious from the continuum. And finally, there is no conclusion, as I said. Okay, so let's start from the beginning, which more or less is going to be the only coherent part of the story, with a message, which is that, I deeply care about the following problem. Okay, so in 2012, we found this new particle at the LHC, which is a doublet of SU2, has a certain hypercharge. But what matters is that its mass is the second most relevant operator in the standard model Lagrangian. And just like the most relevant operator in the standard model Lagrangian, the cosmological constant, it doesn't break any of the symmetries of the standard model that we all knew and love before generalized symmetries came to be known also to particle physicists. And so you can try to estimate its value using just the selection rules of the symmetry of the standard model. Okay, so it's not breaking any of the symmetries that are unbroken in the standard model, but it is breaking some that are already broken. So you can always use selection rules, and you're going to get that this is going to be, so this is a scale, so a scale squared, and so dilations are going to tell you that this is proportional to a sum of other quantities that have the same dimensions. Okay, so this is just dimensional analysis, which is nothing but the selection rules of dilations. If the Higgs had no interactions, so if its Lagrangian was purely quadratic, so something like this, then it would be radiatively stable. And you can see this in many ways. One is the higher spin symmetry that Nathaniel was alluding to before. But in any case, if you want to have corrections to this mass, you need some interactions. And so this is proportional to the largest coupling in the standard model that breaks either the air spin symmetry of the free scalar or the shift symmetry if you think of the Higgs as being possibly a Goldstone boson of some global symmetry. So this, as you can see, I mean, in this estimate, there was nothing going into it except for the most basic principles that always guide us in physics, so dimensional analysis. And it turns out that this number is about 34 orders of magnitude bigger than experiment. Well, the practitioners know that the same happens for the cosmological constant, but in a more dramatic way. So this number here is 10 to the 120. And I would say that there are two interesting aspects to this problem. One is purely experimental. So as I said before, this is the second most relevant operator in the standard model Lagrangian, which means that if you go at sufficiently high energy, it will dominate the phenomenology. So the fact that complex atoms exists, the fact that complex chemistry exists, and the fact that we exist depend on the fact that this parameter is within a certain very small range. Okay? If you move it by an order 1 factor, nothing like that exists anymore. So this object is very relevant to the appearance of the universe as we know it. It's not as relevant as the cosmological constant just because of scaling dimensions, but it's still important. And then there is a purely theoretical aspect, which is probably the one that motivates me most, which is the fact that there are many possible explanations for why this is. This is not a contradiction within the theory, so the standard model is perfectly consistent. However, you still want to explain it, and whatever explanation you can come up with, it will change rather dramatically, or at least qualitatively, the way we think about physics. I'll give you some examples. Well, one is just that there is some new symmetry at some scale much smaller than the Planck mass. And at the moment, the only symmetries that we know can do the trick are supersymmetry or scale invariance. So if you want one of the questions in this talk, if there is more to it than that. Sure. Sure, modulo the fact that so in practical constructions, so if you're thinking about the Higgs as a pseudo-Goldstone boson, what's doing the heavy lifting is really scale invariance. So scale invariance is explaining to you why the strong dynamic scale is much smaller than the Planck scale, or if you want dimensional transmutation. And then the Goldstone nature of the Higgs is buying you a factor of 4 pi. Okay, so. Yeah, but yeah, I mean, I have no problem adding a shift symmetry here.
Very small. Sorry.
A second option, which I'm sure you will not like as much, is that we have a landscape plus a selection mechanism. This means that in some way, to be specified, there's more than one value of the Higgs mass that's realized in nature. There are actually exponentially many, enough that one is 34 orders of magnitude smaller than it should be purely by accident. And then you have to explain why this is the one that we're observing. So one way to realize this concretely is that this landscape is a multiverse, meaning that you had a phase of a long inflationary phase, where you produce many causally disconnected patches of the universe, and in each one of these patches, some fields that once you integrate them out determine the parameters of the low energy theory, they sit at different vacuum. And so they give you different values of the fundamental parameters. In this way, it's easy to get exponentially many values of the X mass. And then you have to explain why. So in most universes, this estimate will hold. So if you take 10 to the 34 universes, in all of them except for one, you're going to find that the X mass is this value. And then you have to explain why you see that one. And there, okay, there is a plethora of ideas for explaining why we live in this unlikely universe. Well, another one is that you lower the scale of quantum gravity. And here I'm really thinking about the dumbest thing. Like you add to your theory 10 to the 34 degrees of freedom. They all couple to gravity. This brings down the effective scale m Planck to m Planck over square root of n. And you get that this estimate instead becomes order 1 of the experimental value. There are many other options. I'm not going to list them all. But the other ones, I would say, are possibly even more radical than these ones. Okay? These are, quote unquote, the conservative ones. And as you can see, they're already telling you something quite dramatic about nature. Either there is a symmetry that we didn't know about, or there is a multiverse, or there are 10 to the 34 degrees of freedom that we have not yet seen. And, well, you can believe me when I tell you that the alternatives are, quote unquote, even worse. Okay? So you might think that the Wilsonian effective field theory picture breaks down at some scale, so that some high energy effects are important for explaining this hierarchy. You can think that gravity in the ultraviolet behaves in some non-trivial way, so it doesn't enter as a threshold in these kind of corrections, but for example, just dresses the S matrix as a phase, as in some 2D example that exists. Or you can think that gravity has no scale, but then you have the problem of introducing a ghost in the theory. Or you can just say it's an accident. Okay? By an accident, maybe let me put it here. Okay? By an accident, I mean that you get to some scale. Okay, so the X mass is here. You go up in energy. You discover some new scale where maybe supersymmetry or scale invariance is realized. So at this scale, you can calculate the X mass. And it's going to be some combination of other mass parameters. At this scale, your experimentalist friends probe all these other mass scales by finding new particles, let's say. They measure them independently of the Higgs boson. You do the calculation of these constants here, and you find that for some reason, even if m1 squared, m2 squared, they're all of the same order, and of the order of the scale that's much bigger than mh, for some reason, you find that all the order 1 numbers in front conspire to give you a much smaller result. But then, okay, if you just find this, doesn't exclude the second one, for example. But I'm just imagining a thought experiment where for some reason we're able to experimentally exclude that this option is there, and you just discover this possibility. Notice that, okay, this might not seem very dramatic, okay, it's just an accident, but it's telling you that essentially the fact that we could make any prediction about nature was just an accident, okay? Because effective field theory works precisely because these numbers are always order 1. If they weren't, all the effective field theories that we had to describe nature so far would have been useless. Okay, so this hopefully convinced you that this is an interesting problem, even those of you that have never seen it before. Do I have something to hit the blackboard? Well. Yeah, thanks. Well, I don't really need it actually, but anyway. Yeah, there's more blackboard than I'm used to. So, okay. So what's the connection with 2 dimensions and the dualities? Well, the connection is the following. So as you probably know better than me, there is a very well-known duality of the two-dimensional Ising model. Okay, let me just take the simplest case. Okay, you have some square lattice. All the couplings are the same. You have your usual Hamiltonian that sums over nearest neighbors. And these are just classical spins, okay? So at every site you have some variable that can be plus or minus 1. And the Hamiltonian is summing just over the 4 nearest neighbor of each side. That's it. I'm even putting the same coupling in front of everything. So in this theory, there is a high-low temperature duality. So one can show that there are 2 equivalent descriptions of the theory. Very schematically, it's not exactly like this, but just to give you a feeling, the duality is telling you that you can invert the coupling, not exactly. Okay, so the relation between the 2 couplings is a bit more complicated. And find some new variables that are some non-local function of the old variables. So you have to imagine this as an infinite product. Okay, so take some spin on some site I, and then shift by 45 degrees and create a dual lattice. Then if my new variable, which is known as a disorder variable or disorder operator, lives on this shifted lattice, then you can draw some path from this point to infinity. And this product extends over all the sites for which there are links that cross this path. Okay? And the statement of the duality is that you can compute correlation functions on this side or on this side, and they are going to be equal provided that you do some operation with the coupling. Okay? And why is this interesting for the hierarchy problem? For 2 reasons. So the first one is precisely that it relates some local degree of freedom on one side on objects that look very complicated and non-local when expressed in terms of the original variables. So it's something that you would never find by just looking at the Lagrangian. So it's something that conceivably we might have missed. The second reason why it's interesting is that the way in which the coupling is affected by the duality, if you map it to the usual Landau-Ginzburg effective theory of the phase transition, it acts on the mass exactly the way we would like it to act. So if you have your phi to the 4 theory and ask what this duality is doing, is essentially switching m squared with minus m squared. And indeed, m squared equals 0 is a special point. And when you get there, so in 2D you get there non-perturbatively, but once you get to the critical point, this duality becomes a symmetry. It's a symmetry that's non-invertible, but for me the fact that it's non-invertible, it's more of a curiosity. Okay? For me, the 2 important features of this symmetry, the reason why I even remotely care about it, are that it does this to the mass, and it's non-obvious. So it's something that might still be there and we have not yet discovered. Now, okay, so this is, let's say, the exciting part. Now, let me immediately tell you, before we go into more details, why I don't think it's going to work. Yes?
So this map you wrote is just schematic, or you mean that is that m equal to 0 is actually a special point?
No, it's actually a special point. So, well, the only schematic part of the story is that the relation between the couplings is this in reality. Where k is equal to beta j. Okay? So the only schematic part was that here I said that you go from j to the minus 1, but in reality, this is the relation between the couplings on the 2 sides of the duality.
In the continuum theory?
Is your question about whether there's something special in the Landau-Ginzburg theory at every
No, there is no.
The critical point is m equal to 0 in some scheme, no?
Yeah, it's m equal to 0, but yes, I mean it's like the full m, not yeah. There is no perturbative way in which you can approach the critical point, at least in 2D.
I also mean, so that this is the continued description of this latest model, and then in the continued description, this is the duality transformation. Was that what you were saying?
So this is just the effective theory of the phase transition. Okay, so it's just a lot of theories map to this. But indeed, so essentially the goal of this talk is to find all the other irrelevant operators, to see if there is anything special once you find the right ones. But indeed, so yeah, in the continuum, that's what the duality is doing. It's also doing something to lambda, not only to the mass, but that's how it acts. A bit away from the critical point.
And here it is crucial that phi is a real rather than a complex field, right? Because then you can hope to have a Z2 symmetry. But if it is a complex phi dagger phi, again you will.
Sure. But I mean, this is just the statement of doing the right continuum limit of this model. But I mean, there are dualities for more complicated models, let's say. Okay, so it's not crucial that you have to start with a Z2 lattice theory, and it will only work with a Z2. That's I don't think that's also. The reason why I don't think it will work is another one, which I'm gonna tell you. Well, it's more than one. Okay.
Can you explain? So in the context of these models, right? So you discussed lattice theory. You wrote some action in terms of phi. So normally we talk about maybe scalar field actions, and then the theory is Gaussian in the UV. Then there is the CFT. And then there is a lattice model. So is there CFT in your picture?
No. So no. What I would like to do is take this model away from the critical point and map it to a theory like this.
What do you mean by map?
Well, essentially, I'm gonna write the following. So I'm gonna write a generating functional that looks like this. And I'm going to show you that it's the same as the partition function of this theory. Okay, and then, so it's just an equivalent description. So I'm going to be able to write the correlation functions of the spins in terms of this quantum field theory.
But is this true only when the lattice is the lattice spacing is going to 0, or for
yes.
every
So this is going to be an effective theory with a cutoff. With the cutoff precisely being 1 over the lattice spacing. Yeah.
So you want to understand how the Kramers-Wannier acts on this description in this Kramers-Stratonovich.
Yeah, exactly. So I want to see if it survives, even if I don't keep all the non-local terms. So I'm not going to do precisely that. Haber-Stratonovich, and then see if, and then just check whether the duality works, if I have to keep all the relevant operators or not, which ones I have to keep. But in practice, so I'm going to stop before. So I didn't get to the end of the calculation yet, so you're just going to see how it looks, but not yet. Yeah, I don't have a conclusion on the duality yet. But okay, so this is what I'm going to do next. But before that, I just want to say why I'm not. Yeah, I don't think it's going to do any magic for the hierarchy problem. Okay, so it's not impossible that in some sense it will be useful, but as I was saying before, it will not change our dimensional analysis expectations. Okay, so let me call these caveats. Okay. So the first caveat is that, as you can see from here, for example, the duality is exchanging beta with 1 over beta. So in some sense, is giving you a high energy description of a low energy theory, and so it's very likely that it will work as a symmetry only in a conformal theory, so that you will have to get to some scale invariant description for this duality to become a symmetry. Okay, so presumably, if we want anything like this to work in the standard model, we will have to turn it into a CFT at a scale close to the experimental value of the Higgs mass. And so experimentally, this is not going to be any better than what's already on the market, okay? Just straight up putting supersymmetry at that scale. I don't think this makes it uninteresting. It's still interesting if it works in any form, but it's not gonna be magical, okay? So life of a BSM theorist is made hard by dimensional analysis, but dimensional analysis, at least in this context, seems unavoidable. The second caveat is that we are in 2D, where there is not really a hierarchy problem. So if you compute, well, let's say you are sufficiently far away from the critical point that you have a perturbative Landau-Ginzburg description, but you are sufficiently close that the continuum limit makes sense. You can do the exercise of computing radiative corrections to the mass of the scalar. And again, dimensional analysis tells you that they're going to be logarithmically sensitive to your UV scale. So if you want here the lattice spacing. So even if you take this cutoff of the theory to the Planck scale, you're going to have no problem. So there is no power law sensitivity of the mass. This is not necessarily, again, a problem of this whole program. It's just telling you that maybe when you're going to find something like this in 4 dimensions, it's also going to apply to marginal couplings. If you want, it ties back to the CFT story, but more broadly, it ties to what we already know about this kind of dualities in 4D. So if you want, Seiberg duality is kind of similar. A bunch of these dualities in electromagnetism at fixed value of the gauge coupling are very similar in spirit. So maybe once we get to 4D, we're just going to find a story for marginal couplings. Finally, well, the last caveat is to me also a reason why I think this program is interesting, which is that the dualities like this exist also in higher dimensions, but they never become symmetries. So for example, in 3D, they relate this classical theory of spins to some gauge theory on the lattice. And in 4D, they relate them to some theory of an object with 2 indices. So when you go to the continuum, you're going to have a duality between a theory of a scalar and the theory of a spin 1 object, and the theory of a scalar and the theory of a spin 2 object. So they never become symmetries, so you cannot hope to explain the hierarchy problem with them, but maybe they become non-trivial dualities that are just interesting in themselves. So, okay, so.
Raffaele,
Yes.
can I ask about your first caveat? So this may be that the symmetry is exact only in the context of a CFT, but we talk about soft breaking all the time, including in supersymmetry. So why couldn't you imagine that a remnant of this would still be effective if you have soft breaking of conformal symmetry?
No, that's entirely possible, but then you're not qualitatively changing the picture compared to saying the standard model. I mean, you're not easing the experimental tension that we're seeing today. That's all I meant. I'm not sure if. So I'm not saying that this makes it impossible. I'm just saying that it makes it no better than just supersymmetry or normal composite Higgs. That you would still expect new states at the usual scale. Yeah, that's all I'm saying. That's what I'm saying. Plus, well, plus the added ugliness, if you want to really make the standard model conformal, you have to add a lot of stuff at that scale. But yeah. Okay, so I think I've taken way too much time for the introduction. Now, well, yeah, let's be more concrete. Well, Slava kind of already told you exactly what I'm gonna do, but for those that not seen this before, I'm gonna do it in a little bit of detail. So let me start in 1 dimension. So in 1 dimension, the duality is very explicit. It's just an exercise of polymatrix algebra. So now I'm on a line. So these sums just extend on a single line. And, well, my Hamiltonian, however, depends on time. Purely for simplicity, just because I want to state the duality in one line on the blackboard, I'm going to assume that, that we're on a circle. And that also time is Euclidean and it's on a circle. Similarly, for simplicity, I've normalized the magnetic field of this transverse model to 1. So you can think of my Hamiltonian H as actually being the real Hamiltonian divided by the magnetic field. But again, this is just to make everything more streamlined. It doesn't change anything. Okay, so in this theory, you can define the following variables. I'm going to drop the dependence on time when it's obvious. And I'm also going to drop the ats. These are all operators acting on some Hilbert space with two states, with two states as a basis. Okay, it's easy to check that these objects have the exact same algebra as the polymatrices. It's really an elementary calculation. And you can also verify pretty easily that if you invert this relation, sigma 1 is going to be the following. Let me just not make... yeah, sorry. And for the duality to be so simple, it's important to be on the circle because essentially when you want to invert this relation, it's useful that when you go back around, sigma 1 squared gives you 1. So that's why the expression for sigma 1 in terms of the muse is so simple. And you can see, well, you can see two things immediately. One is that I kept my promise, so the new degrees of freedom are some non-local combination of the old ones. And also that I can rewrite my original theory in terms of the new degrees of freedom and obtain something equivalent. So if I factor out lambda, I'm just going to have the following. Okay, well, it's very simple to see because sigma 1 becomes mu3 times mu3, so this term, and sigma 3 times sigma 3 becomes mu1. So it's, in some sense, a trivial identity. And you can see immediately from here that imagine that you have some eigenstate of the Hamiltonian that at some critical point it becomes 0. Now I have these two equivalent descriptions, the one in terms of the sigma at lambda and the one in terms of the mu with the following Hamiltonian at lambda to the minus 1. So this means also that at the critical point, this is also true, which is telling you, well, just that the critical point is lambda equals to 1. Okay, this was all very simple. I've done this exercise that's probably well known to some of you to make the duality more concrete to those that are not used to it. It's also simple to show that it's non-invertible. You can do it by, for example, writing the spin flip operator, applying the duality to it, and showing that if you assume it's invertible, it's an invertible operator, you get a contradiction. I'm not going to do it because I went way too slow on the introduction. And now, well, what we want to do is to do some continuum limit of this model and see what it looks like. Yeah, so as Lava said, I'm going to use Hubbard-Stratonovich, so which is just a fancy name for a standard trick of Gaussian integration. Okay, so I have my, I'm just going to do it for the partition function for now. So I have my original partition function in terms of the polymatrices, which is quadratic. For now, let me drop the magnetic field just to show you the trick, and then I'm going to put it back in. Okay. So if for some reason I wanted to compute the partition function just for this, I could simply do the following. So let me call J a matrix. This is just telling you that it's coupling nearest neighbors also for the sky variables. And there is a sum implied over all the indices. Okay, so I'm summing over I and j and also I here. Well, if you do this Gaussian integral, you're going to see immediately that this is nothing but sigma I, j, ij, sigma j. Still summed over the indices. Okay, so I can use this simple trick to write my original partition function as a path integral. And well, I can do it also with the addition of the transverse magnetic field. I'm going to do it in a second. So the reason why it's going to be useful to do this is that you're gonna, once you do this, you can trace on a single variable, and there it's trivial to do the trace. So in the end, I'm in practice turning the difficult part of the trace into a path integral, which you can argue it's words, but well, I'm trying to learn something about a new theory. That's why I'm making my life more complicated. Okay, so let me add back the magnetic field. And of course, all these variables depend on time. I'm just not writing it for not to take one more hour than I'm allowed to. And so here I'm just going to do exactly what I said. And again, I'm leaving sums over this index I and j implied, okay? But I'm summing over everything. And I still have the trace, okay? So this part is independent of sigma, so I can insert a complete set of states here and split this into two traces. So I'm just going to do explicitly this part. And sorry, I forgot that here there is still the integral over time. This is going to be important. Okay. Now note that operators at different sites and at different times, again I should keep the integral, commute with each other. So I can write this exponential of the sum as a product of the traces of a single matrix. Where this matrix is just chi minus chi h h. I can diagonalize it and do the trace, and I'm just left with the following. Okay, so at this stage you already see that this doesn't map to any relativistic quantum field theory that you care about. It's actually mapping something to something that's quite nasty and non-local in time. But yeah, let's get to the end, because the exact same steps then are useful for the model we actually care about that I'm going to do next. So now I can plug this result back there and factor out a 2 to the n, which I'm not going to write, so it just goes away in the correlation function due to the usual normalization factor. And then I'm left with something like this. Okay, so this is the result. Now, well, it's not hard to go to the continuum limit. You can just define a scalar normalized like this, which was okay. So we are gonna just call this some point. And well, we're going to use that this is just really a nearest neighbor interaction on the line. So in the continuum, it's going to look like this. And for small lattice spacing, it just gives you, well, the kinetic term that you expect plus higher derivative interactions. It turns out that's actually easy to resum these higher derivative interactions, and the way the object looks like is this. Sorry. Yeah. I don't know if you can see it, but it's just some hyperbolic cosine of a space derivative divided by the UV cutoff, which is the inverse lattice spacing. So finally, if you want to put it all together in one expression, you're going to have the following theory. Notice that this integral, I mean being a bit glib on the continuum limit, you see, because this normalization is such that you have a factor of a in front that you can use and that I'm turning into this differential, and then I'm turning the sum into an integral. But apart from that, yeah, I'm doing nothing bad.
Raffaele, may I
Yes.
ask you, are you going to use this as an effective field theory? Or?
Yeah, well, yes, so that's the question indeed. So This one in particular, I'm going to probably ignore because of this kinetic term. Sorry, of this of this kinetic term in time. So the whole point in the end is in what form does the duality survive? Okay. So first of all, I could have done this exact same exercise adding a source. Okay. Could have added plus some j sigma 3, for example, and then I would have gotten some j squared here. Okay. So that now I can use this to generate correlation functions on the two sides. So I know how to compute correlation functions for the spin in this description. They're nasty, but I know at least formally how to do it. I don't know. I just take derivatives with respect to j, and I get some expectation values of hyperbolic cosines and stuff like that. And so now, okay, so you compute that correlation function, assuming you can. And then you compute the correlation function for the disorder operator. The way we want to do it, as Clay suggested, is to use, let's say, the canonical perspective on the disorder operator, so as attached to this line that flips the spin. So we're going to solve the equations of motion for phi with boundary conditions such that it changes sign across this line, plug it back in plus fluctuations, and compute the correlation function for the disorder operator, and check if they're the same. So as I said at the beginning, there is no conclusion because that's the part that we have not done yet. And so the whole question is, once we do that, are we going to find that the correlation function of the spin and the disorder operator are the same only if we keep all higher derivative terms? Or is there a simplified version of the duality in some limit where either phi is small or the derivative over mu v is small that still works? Okay. So the dream is that this is true, that you don't have to keep everyone here, because otherwise, as you and many others here are very well known, this is a terrible theory with a ghost.
But can you explain it? Why for example, you already had this sigma description in terms of sigma degrees of freedom. So now you decided to pass to this phi. So what?
Yes.
Is it just because you like the field phi which runs from minus infinity to infinity? What's the motivation? Why, for example, you couldn't just perform some coarse graining on the original theory and you would get also there some coarse grain description in terms of phi, some phi?
I could. I mean, I'm just checking if these dualities tell us anything that we don't yet know in the continuum. This is the continuum limit that for me was
limit because it's still such a cutoff theory as the original theory. It has precisely the same cutoff.
Yeah, I mean,
why is this continuum? It just has a field running from minus infinity to infinity, but unless you tune the couplings, it still has a mass gap of the order of the lattice scale. So
sure. Yeah. No, this is all true. I mean, I said at the beginning why I don't think we're gonna really be able to carry it to the hierarchy problem. Now I'm just asking, is this lattice duality teaching me something about effective field theories that I didn't know before? So
why in this language? Why not in the original language? Why couldn't you ask this question in the original language? Like you could, for example, add some coupling to the original theory.
Yeah, I mean, indeed, you can do it in different ways. I'm not sure yet whether this is going to be the one which gives me a result. This is our first attempt. I mean, as I told you at the beginning, we have no conclusion and no broad message for the moment. So the only reason why we chose to do it this way for now is because it was the easiest way to keep all the irrelevant terms and then check explicitly if they matter or not. So indeed, I mean, I don't know, maybe doing the continuum limit in another way is better.
So is the wonderful goal to find a feature that is not obvious in the continuum this continuum description, which nevertheless is a manifest explanation in the lattice description.
Yeah, you could say that. Yes, yes. I mean, to me, let's say the key question is, can I see a form of the duality even without keeping all the derivatives?
Yeah. I mean, in your previous example of Ising the spin thing, right? Like extending the m squared to minus m squared. Then we could have seen in the already continuum limits in a self-contained manner too, because there's a Z2 symmetry I can impose on that, and then they may explain why, in other words, that m squared is technically natural, right? It's a charge under Z2.
Well, no. This is not. No. The m square is invariant under the Z2.
No, Z4.
What's that for?
You mean the dual? Yeah.
So that's what I brought up. That is a complex versus the real scalar. In the real scalar, that you can find the subcontent explanation for that smallness of m squared in that theory, which is Z4.
Well, but that Z4 is just the duality I'm talking about.
Yeah. So in other words, I'm saying that there's actually a phi square operator charged under a normal kind of symmetry, which is Z4 symmetry.
Well, in some sense, well, yes and no, in the sense that really, if you go at the critical point, you have some primary operators that transform under the duality, but. Sorry?
Yes.
In this discussion, phi is a real scalar, and phi squared is not charged under any standard invertible symmetry.
Phi squared is charged under Z. So it is a Z4 breaking spurion. M squared is a Z4 symmetry breaking spurion. What is Z?
I don't understand what Z4 you are talking about, I think.
Oh, sorry. I forgot.
Yeah.
I missed that. Sorry.
Okay. Yeah. So, there is a symmetry, but it is the duality I'm talking about. It's not a normal Z4. Okay. So, yes. So as I told you at the beginning, there is no conclusion, but you can repeat this exercise for the classical 2D easing, and well, essentially you're gonna get the same result. So I'm not gonna redo all the steps, except that now by construction. So here we kind of knew from the beginning that you would have encountered something like this, because this transverse easing model is a continuum time limit of a 2D model where the lattice spacing in the time direction and the space direction is very different. So they're even exponentially different. And so you could have expected to obtain something that looks like this. So not at all a relativistic looking kinetic term. Instead, if you start from the classical model, so really the simplest thing you can imagine, where now these sigmas are classical spin variables and your sum is over the 4 nearest neighbors that I drew at the beginning. Then, in this case, this hyperbolic cosine that, if you remember, was coming from this matrix pairing nearest neighbors is going to be symmetric in the time and space direction. So you would not be surprised to see that if you repeat this procedure, you're going to get something like this. So we're still in the Euclidean, so so I'm going to write it very schematically, okay? Now let me just get the factors of the couplings right. So. And similarly, you can add a source that just appears summed to phi and compute all the correlation functions that you want. And so for now, we got here. So the next step, of course, we know how to compute the correlation functions of the spins. And the next step is to compute the ones for the disorder operators and see what happens. Okay, so see how I'm doing on time.
So, do you still have, so phi is a function of, so two-dimensional, x is a two-dimensional vector, but then is there lots of time or not? Or am I missing?
Yeah, so let's say you're in the Euclidean and one of these two dimensions is time, and phi is a function of both, and this nabla squared
Because I thought
is
that,
just dx squared plus d
I
tau.
thought that the Pauli matrices, that the spin variables that you have, they are living in a one-dimensional lattice. So that's, but then they're also dependent on time.
No, now these are just
They have time independent.
yes.
But before they were dependent.
Yeah, because before I was mapping before I was mapping a two-dimensional model with let's say space. Let me do it. Let me do it this way. Okay. Very schematic. So before I was taking the same model, but with a different coupling in space and time, and then there is a standard procedure to show that it maps to this one where the matrices depend on time. Instead, here, let's say both the space and time dependence are encoded by the indices on the two-dimensional lattice. So that's the only difference. And so, well, this guy looks superficially promising from an effective field theorist perspective, and we want to check how the duality looks like. You can make some initial checks by computing how the mass is renormalized in this theory, but you won't be surprised to know that nothing special happens, okay? Because the approach to the critical point in 2D is non-perturbative. So if you try to compute corrections to the mass using this potential, you're going to find a series that actually does not converge, okay? Some of you were at IAS when Nima said that this story was nothing more than saying that logs with this potential resum to something finite, but that's not true. Okay, so if you actually compute, so you can expand this potential. And you're going to have a tower of phi interactions. And it's easy to compute the leading log corrections to the mass. They come from diagrams that look like this. And so on. And so you're going to get some series that looks like this. And you can check by computing the coefficients that this series doesn't converge. So unfortunately, there is no trivial check that something special is happening at the critical point. You can similarly compute some Coleman-Weinberg potential from here, which we did, but again, you obviously get the same result. So to conclude, as I said, for now, there is nothing definite that I can tell you that you would find particularly interesting. Just purely as a practitioner of BSM, what I found curious about this exercise, which however was probably already known to some of you, is that, well, you can start from a trivial lattice model and get out a complicated interacting quantum field theory. Again, this was well known, but if you think about it from a reductionist perspective, it's quite fascinating. Okay? It might be that all the complicated interactions that we see in the standard model actually come from something much simpler on the lattice, that we're just seeing at low energy as a more complicated interacting theory.
Raffaele, how
Yes.
much the duality transformation acting on the phi description? Unless you have said that already.
Yeah, so it's yeah, so I don't think that I can tell you, but I'm not sure that computationally this is the best way to go, in the sense that forget about the transverse, okay? And just look at at this, let's call it action, okay? So I can compute the equations of motion, and I'm gonna find that chi is equal to this, okay? which is just J, the sum over the nearest neighbors of I. So in some sense, okay, chi is proportional to phi. There is just some rescaling in going to the continuum limit. But effectively, this equation of motion is telling you that phi is measuring some sort of average magnetization. So it's not the same as the mean field theory. Okay, so you can check there are order 1 differences compared to mean field theory, and also there are a bunch of higher derivative operators that make phi different than the mean field theory phi. But effectively, it's proportional to some sum of the sigmas. Okay, you know that mu is this infinite product over some path of your choice to infinity. So in practice, you can work out the relation between phi and mu also in the continuum, which is the same as the one between sigma and mu. So the dual phi, let's say, sorry, it's an infinite product of the all phi's. But as I was saying before, I think that the best way to actually compute the correlation functions is to remember that mu is attached to a spin flip line. Okay, so you want to solve the equations of the classical equations of motion for phi with this boundary condition that it changes sign across this line. So you put mu, say, at the origin, and this line is implementing the Z2. So you find a classical equation of motion that that respects this boundary condition, and then you put it back in the path integral and you compare it to the calculation of the normal 1 or 2 or 3 point function of the spins. Okay. Notice that, okay, I'm telling you this to give you a simple picture, but in reality, the way in which you compute the correlation functions on the sigma side of the duality is by matching generating functionals. Okay, so you can match generating functionals, as I was saying at the beginning, and you're gonna end up with some source here, and derivatives with respect to this source give you correlation functions of sigma. So for example, if you want, I don't know, sigma sigma, yeah, you're gonna have 2 derivatives with respect to your source. And it's going to give you some expectation function of 1 over hyperbolic cosine of phi, 1 plus 1 hyperbolic cosine squared. Okay, so this is, well, actually this is the 1 point function, I think. So in practice, you're going to do this. So this is going to give you the 1 point function of sigma on one side of the duality, and on the other side, you do this. And I don't know yet, I mean, I doubt that you can do the mu part analytically, because look at the potential, but we're gonna try, let's see.
I was just curious, from the perspective of the lattice duality, do you have any expectation why some of the sort of operators in this continuum in quad description is not getting renormalized or suppressed?
So are you asking if I expect something special to happen to the mass here, or are you asking if I expect that I can drop some irrelevant operators?
Yeah, because in one of the previous example, you see already that on the continuum limit, right, phi squared is a charge under Z2 non-invertible symmetry, and therefore you have a symmetry explanation why this could be suppressed. Or if you're sitting at the critical point, maybe you go for 0.
Can you explain what you mean by continuum limit? Because you see saying continuum limit irrelevant operators is just, to me it makes no sense, because when you talk about relevant operators, it means you are sitting next to some fixed point. Which fixed point are you sitting next to? Is it the CFT? Is it the Gaussian theory? When you talk about continuum limit, do you mean that you are reaching a Gaussian theory continuum limit or CFT continuum limit? I'm completely...
Okay, yeah, sorry. I think it was just a matter of language. So I'm hoping to describe the duality near the Gaussian fixed point, okay? I want to check if that works. Because if you want, I'm matching this theory to my to my discrete one at the UV cutoff of this theory, okay? So this theory, I can match it to the lattice at MUV. And then if I keep all the terms, I have done nothing, okay? I agree. I just have a different description of the lattice. I'm calling it continuum limit loosely just because I'm writing down fields, not for any other reason. What I want to know is, let's say I do some power counting expanding at small energy with respect to the inverse lattice spacing, will I still find the form of the duality or not? So that's the question. Probably not. But
are you trying to just, can you reformulate it by saying, let me look at free theory in 2D, free scalar theory in 2D. Does it have non-invertible symmetry or not? Is this the question?
Well, not exactly, because I'm willingly to keep all the non-derivative interactions.
What is the when you didn't reach any continuum limit, and your theory has a cutoff?
Yeah, my theory has a cutoff, but that's what I find. I mean, I have the impression that we're just arguing about language, okay? So I want to know if this effective theory has the duality or not, and if to see the duality I have to keep all the irrelevant operators or not, okay? And by irrelevant, I define them from the free theory.
And why is the, since you have a cutoff, why is this potential term somehow, you want to keep the potential term, but you want to drop these other interactions? Everything is in the same footing if you have a cutoff.
No, indeed. I mean, I don't have a priori an expectation that one is more important than the other, okay? So I just want to check what I need to keep to see the duality.
I think the answer is obvious. It's a very delicate property of the theory you started with. You did some very complicated transformation which completely obscured this property. The moment you drop anything, it's all lost.
Well, I hope you're wrong. You might be right, but I hope you're wrong. Well, we're gonna check.
I'm willing to bet any amount of money.
Okay. As I said, yes.
Can I phrase the question this way? Say we are at the critical point. We have this non-invertible symmetry, and we know that at least in this lattice description, away from the critical point, there's something that survives, which is some duality between like this height and fidelity. You have this scalar field theory. You know that at the critical point there's this non-invertible symmetry that once I turn on any interactions going away from the strongly coupled, this is gone. Are you saying, okay, is there a set of deformations where now instead of this non-invertible symmetry, I have some duality? Is that the question?
Yeah, essentially, yes. I mean, I'm not expecting to recover this symmetry. Also because I'm never leaving at the critical point. All I care about is the duality, indeed. Yeah, so I don't know, Slava, you have the same opinion about that as well, but yes, my hope is that you can recover some form of the duality. But okay, as I said at the beginning, and as I've written down, I'm not sure that this is going anywhere, maybe not. Actually, I wanted to stop, but Clay convinced me to continue, so you can get angry at him if you think that's obviously gonna fail. So I think we got to the no conclusion part. Well, very broadly, as I said, I find fascinating that you might think that maybe the complicated theories we see in the standard model as effective theories are really much simpler lattice versions. I still have the hope that I'm going to see some form of the duality in this theory, and maybe it's interesting, maybe not. Let's see. And finally, well, going from 2D to 3D and 4D will definitely be more complicated and will have nothing to do with mass hierarchies, but it's potentially more interesting in the sense that it's going to relate some theories of scalars with some theories of spin of fields with spin. Okay, so having said this, I can stop.
Okay, so we're a bit over time, but I think we have time for one or two quick questions, if there are.
Can you explain what you mean by the standard model being complicated theory? Because it sits next to free theory, right? It's just a small perturbation of free theory. So, I mean, I love the Ising model, but it's not nearly on the same footing in terms of simplicity. It's just a very dirty pile of shit compared to the standard model. So how can you be fascinated?
No, I think we're going back to semantics. I mean, I find what I call simple in the Ising model is just that it's a quadratic Hamiltonian.
But it's a strongly coupled theory. Well, the model is a
it's a strongly coupled theory. No, I mean, I can choose if I want to make it a strongly coupled theory or not. So it's a strongly coupled theory at the critical point. But I mean, you're assuming
of the order of the lattice scale.
Sorry?
And away from the critical point, it has cut off. It is not rotation invariant.
Yeah, sure, but no. I mean, it's a cutoff if you think of it indeed as a continuum effective theory. But if the lattice model is the lattice model, I mean, again, I think that this discussion is stupid in the sense that what I call simple is just a model that has a Gaussian Hamiltonian, okay? And if it wasn't like...
It's not Gaussian because sigmas are variables plus or minus 1.
So sorry, I shouldn't have said Gaussian. So what I meant is what I said before, that it's quadratic, okay?
It's quadratic. And this is quadratic, but it has a very strong nonlinear constraint that sigma equals plus or minus 1. It's a very complete.
But I mean, sure, but I'm not saying that I don't want to map the standard model as is to the Ising model. I'm just wondering if some of the interaction of the standard model could come from purely quadratic terms, okay? So it's a very vague question, and I'm not planning to go anywhere with it, okay? But I think that we're just arguing about what we call simple.
Okay, any other quick question or comment? If not, we can thank Raffaele again.